Afternoon, everyone. First up, as I start off, I have a question for all of you. The key point there is how many of you identify yourself as millennials? Quite a few of you in the room. You'll resonate with what I'm going to say next. How many of you identify yourself as Gen Z? Pretty much a good makeup in terms of what we are seeing outside also. The reason why I bring that up is what we are going to talk about with respect to a playbook for a greener cloud migration. And you're probably wondering, why the hell is Sherlock here, Neo for Matrix, and why are they playing Tetris? What we did want to highlight was years ago, when I didn't have white hair, uh, data storage was extremely expensive. I could only put 2 wallpaper images of my favorite actors in a 1.44 MB floppy disk. When we did game programming, every bit counted. Over the last few years, storage has become a lot more cheaper. It's easier for us to take 10,000 selfies and keep on our phone without it pinching our pockets, that we have kind of forgotten some of these data compression techniques. With AI, ML coming into play and the huge focus on, hey, we need all our data on the cloud. It's sitting on premise today. How do we get it all over? It becomes easier to just dump that data over and leverage it. But here's a chance for all of us to kind of be more climate conscious, understand not just the commercial cost as an organization when you're moving data over, but even the cost this planet is taking over. So what we have done is we have worked through with a couple of algorithms that we have come up with, primarily named Sherlock, Matrix, and Tetris, which is how they all tie into this particular image. And the use cases are varied, so we're going to give a few, but hopefully that inspires you to start thinking about it in your domains, in your spaces, and identifying which is the right compression technique, because you'd be surprised with what the savings that can be achieved as an organization and as humanity as a whole. Right? I mean, compression is pretty straightforward. Today, the volume of data that you're moving, there's a cost involved with it. If you compress it, there's a lesser cost. I mean, that's basic math, so we're not going to deep dive into that specifically. But by reducing that particular footprint, and then oftentimes a lot of that data is like how when we do house cleaning, especially around festivals, you kind of just move all the stuff that you have saved for later, move it to the other corner, dust things up, put it back saying, I might need this later. 40 years later, it's still there, that you might need it later. Because we do not see data day in, day out, we do not realize that cost on premise. But as you move to the cloud, that is going to pinch you. We have an entire industry on that called FinOps, to just highlight how important this has become. And this is our small way of highlighting those particular algorithms that we have in place. Each is specific to a use case, but I'll let my colleague Nutan sort of deep dive to a couple of them.
Hello, everyone. Good afternoon. Let me reiterate a couple of things which Vivek has already mentioned, which is why we have come up with these algorithms and what made us to come up with these. So the core idea behind this was how smarter compression can help us move data faster, cheaper, and more importantly, more sustainably. And most of the cloud migrations don't struggle because the computation is slow, but because the data is very heavy. And heavy data means 3 universal truths: slow transfers, higher storage cost, and even higher carbon footprint. Basically everything which your cloud budget does not approve of. And that's when we asked ourselves, what if we reduce that data weight without losing its accuracy even before it starts its cloud migration journey? And that's what inspired us for these algorithms. And let's deep dive into the first algorithm, which is the Tetris compression. How many of you remember the first slide where Neo and Sherlock were playing the Tetris board? only few. But let me remind you, there was this video game where pieces would fall from top and we had to clear the rows. Now, how many of you remember? Much more. So this algorithm also works on the similar way. Basically, let's see how can we visualize this algorithm with the simple example of employee table. I'm pretty sure each of us have, at some point, even in college, we have worked on employee table where we usually have employee ID, department, role, status, etc. columns. And let's imagine a few rows like this. Employee ID 1, role is HR, department is HR, role is manager, and status is active. Employee ID 2, HR, assistant, active. Employee ID 3, IT, engineer, active, etc. Now, what if I change these strings of HR, manager, etc. to numbers? So, if I convert HR to 1, IT to 2, then this column would be the numbers 1/2. Then manager as 1, assistant as 2, and engineer as 3, then this column as well we have converted into numeric grid. And employee ID, everyone knows, is just an increment of the previous row. So those are the clear patterns we have in our table. Now, once I have completed this grid setup, which is my string to integer conversion, I have a cleaner numeric grid of my table. That's when comes the second step. The first step itself will reduce your data size in multifolds. Now, when I come to pattern discovery, we can, there are clear patterns, right? First column is an incremental, the equal delta with its previous row. All other columns, if we can create the similar size blocks, similar to Tetris grid, then at the end of the scan of this particular table, we will know that our table looks something similar to Tetris grid with blocks. And in the scan, if we get that particular block again, we will not store that block in other location. We will just reference that block. So it's the game of discovering that pattern, which frequently occurs. Now, once our table is scanned, the ultimate product is our Tetris grid with tightly knitted data blocks, basically. This compression algorithm actually works on pattern-heavy data. For real-life examples, could be logs or telemetry or metrics data, where each line could be different, but the patterns are same, say timestamps or log patterns. So that's where our Tetris algorithm will work, where you can figure out the frequently occurring patterns. Next slide, please. Okay, so that's what we have covered, where we now, with this scan and conversion of blocks, what will happen is our I/O will be faster, and the storage will be less, and more importantly, our carbon footprint will be reduced significantly. Now that we have learned about Tetris compression, let's move ahead to Sherlock compression, where Tetris belongs to shapes and patterns. Sherlock belongs to relationships. For example, if you want to store city, state, and country, if you have city, then you can deduce the state and country by itself. And that's where Sherlock comes into the picture and asks, if I can deduce some of the columns, I don't need to store these columns. Let's take the step back and take the same example of employee data here. Now, if you remember, the data is somewhere related, where if department is HR, the role should be assistant or manager. If department is IT, then role is engineer. Now, what Sherlock thinks is, if I can store some way the rules that these are interlinked, then I don't need to store the entire row itself. So it goes row by row, And with these observations, it creates the rules. So first rule it created is if the department is HR, the role would be manager. Now when when it scans the table, for the rows where the department is HR and the role is manager, it will store this as a rule. But as soon as it comes to the department as HR and role as assistant, it will say, that's an anomaly. So now let me store this into an exception. So ultimately, at the end of this scan, we will have set of rules and set of exceptions. And this logic will reduce your size further. And these are typically used in anywhere where the columns are meaningfully related, say forms and surveys or relational data or transactional tables. Now that we have decoded Tetris and Sherlock algorithms, let me hand it over to Vivek to explain you the matrix algorithm, our own blue/red pill.
I know this is like right after lunch for most of you. So as we swallow the blue pill or the red pill, matrix reference, the matrix compression works really well when you're dealing with numbers. So if you're in the financial services industry, you're dealing with IoT, you're dealing with large volumes of data, could be calculating data by second or by any unit of time, and you're looking at patterns. It is an extremely mathematical compression algo. This itself deserves 45 minutes for people to understand, which isn't going to happen here. So we are going to obviously be around. You can reach out to us later on. We're happy to talk through it. But I do want to give everyone an idea in terms of how many of you are interested in artificial intelligence or machine learning. Okay, the rest are basically sleeping. As we were working through machine learning and, we talk about predictive analytics, we talk about AI being able to extrapolate. What is that basically behind the scenes? It tries to identify a pattern, a formula behind that series of numbers, sequence of numbers, and then be able to extrapolate that across to say that if Vivek scored 10 runs today, he scored 11 runs tomorrow, 12 runs day after, probably might score 13 runs the day after that, right? And you kind of identify a pattern that, okay, if y-axis is the number of runs and x-axis is the day, so day plus 1, so you've got incrementing from that perspective. Compression in series of data is basically that, identifying that pattern. It could be a numerical, a quadratic equation. It could be variation, mean, sigma, using a lot of these techniques to identify that pattern, store the pattern, and then be able to recreate. There will be exceptions because if anyone's seen clean data, they're clearly living in the matrix. Because in the real world, data is never clean. And that's where managing those exceptions is another table that you kind of mention and store, but you hope that your data is not as dirty as the complete data set. So from that perspective, the overall volume of data that you're hosting and saving is a lot less than the actual data set when you're dealing with patterns. Now, one thing to make sure that we've highlighted through all of this is there's a very key critical concept called lossless. When you're recreating this, because when we're compressing data, we are losing data. How critical is that minute pixel? If that changes, does that change anything? If I lose a couple of rows of data or it's in the threshold, does that matter? That is an important context that you have to decide for your data sets before you choose any of these algorithms. If you can afford, like a lot of times, we have these 84 megapixel, 128 megapixel camera that take photographs. But 90% of the time, we share it via WhatsApp. On the small screens, you don't need an 11 GB photo to be shared on WhatsApp. So it compresses it without changing it dramatically where suddenly I start looking like Shah Rukh Khan. Never going to happen in the real world. But by removing some of those variations that still looks like me, the data size reduces, you get the same impact. So it's very important to understand the context in which you're using that data and how you're compressing it. So like I said, the matrix compression, very focused on using some of these mathematical formulas to identify that pattern and be able to store that data. Now, we spoke about these various compression methods that we have at play. We tried this with a lot of the data sets that we had, and while it can go up to a maximum of about 73% compression of data, on an average in the real world, we saw with the data sets that we were working with, we saw it range between 35% to 50%, which is still a big win. To give you context, we realized that if we did data compression on the data sets that we had, the amount of CO2 produced or would be saved is about the same amount that 22 million vehicles would create in a year. I know none of you are math geeks over here like me. So what does that 22 million vehicles mean? The entire NCR region, which unfortunately is facing an AQI issue, imagine that entire region had zero input of pollution from vehicles, because that entire region has 22 million registered vehicles. That's the amount of pollution / carbon emissions we would reduce just by the data sets that we were looking at. Imagine if each one of us, even at 30% efficiency compression, move the data sets that our organizations, enterprises are looking at, and had a 30% reduction. That just makes this environment, this ecosystem, a lot more better. The previous session was synthetic data creation. I have my own perspective on that, because data creation equals data storage. So we still need to be very, very thoughtful of what data we create, what data we store, and how we leverage that. There's a whole other scope of ensuring, are you deleting data also? That's something that we often don't tend to think about. Again, probably beyond the scope of this conversation we are having, but these are concepts and the philosophies that we sort of wanted to bring up in this audience. Hopefully all of you can spare a thought about it, take it back to your organizations, to your households, and see how all of us together can make a difference, leveraging technology and our own conscious. The impact, it's pretty self-explanatory, as we've already discussed, in terms of savings, in terms of sustainability, and more importantly, all of this has to be explained as a business value proposition to your organizations, because at the end of the day, organization is running a business. And this does add value there, because the cost of hosting, moving that data becomes lesser when you're dealing with lesser data. If you're working with lesser data, if you're leveraging it for ML models, if you're leveraging it in the artificial intelligence world, where again, you're looking for patterns, you're looking for trends, you're trying to forecast, predict, cleaner, lesser data that is meaningful enough is going to add more value than trying to, in that entire rubbish, trying to find that insight that will really help you. Yes, with that, like we quickly mentioned, each algorithm here is specific to a particular use case. You need to figure out which use case works best for you. You can't blindly use one algorithm for all your use cases and expect that level of savings. While what we shared with you are algorithms that we came up with as we wanted to play around and identify unique use cases, there are existing libraries out there which are already very good for specific use cases. A lot of us have used zip, gzip in the classic file format when we were sharing with friends. You know, I told you at the start how the wallpapers that I want to save, I could save only 2. Zip was such a lifesaver because I could save 4. So compression helps from that perspective. There are gzip, zstandard, a lot of those available. As I mentioned, look at which one makes specific use case for each one of you. With that, if you have questions on the algo, the code, the efficiency gains that we have had, feel free to connect with us on our LinkedIn profiles, and we'll be around to have more conversations.